greetings. In this one, I'll quickly talk about why when there's a walk on a graph, there's also a path between the same points. And so a walk, if we have some graph, let's say something like this. A walk allows you to revisit the same edges and vertices. And so, for example, if I say I want to go from vertex U and the vertex V is here, I can take a walk that will go across this vertex, then it will go back through U again, and that will go this path, and now it will go straight. So it will take some unnecessary steps and make that journey longer from U to V. But with a path, we are not allowed to repeat vertices and edges. So let's now talk about the idea that if there exists a walk for any UV in the vertex set of the graph, so this is the graph and the vertex set are the vertices of the graph, we see that for any walk UV, there is this walk UV between U and V, then that implies there also exists path UV. And let's see why. So if I want to draw a line that denotes the abstract notion of the walk, it's U to V. So a walk is allowed to repeat the same vertices, repeat the same edges, so I can go to here, then I go here, I am already repeating the U itself, I also repeat this edge. And a path is not allowed to do that. So there is either a path or a shortest path. Path is simply not allowed to repeat the vertices and edges. So we can go across these. It's longer than going just across this one. And of course, I'm not taking this one in either case. Now thinking about it again. Because this I'm not considering, not even the idea of repeating, but these are both paths. For this one is a path. If I went here and then return and repeat this one, and I'll also repeat this one, I'm already repeating vertices, repeating edges, not longer a path, it's a walk. But what I'm saying is, if we have a walk, so a path can be actually also unnecessarily longer, because if that graph allows it to not repeat the same edges and vertices and still travel to that destination vertex from the one we begin with that walk, it's still a path. As long as those things on the way are not repeated. But if it's a walk, we can also repeat. So for example, I can say this vertex, I'll name this one. This is named U, this is named V, but I'll name this one 2, and this one 1, and this one 2. So my possible walk is U1, 2, U1, V. I go like this. So I've basically been to 1 twice, and I've also done the edge U1 twice, and I've also been to U twice, basically. So U twice and 1 has been twice. So that's a walk. I've been allowed to repeat it. Now let's talk about the main point of what we're talking about. So if we have a walk from U to V, and let's say I'm considering the case on the bottom here, U to V, or any graph, what causes it to be a walk but not a path is when some things are repeated. That means, in general, that there is some extra vertex that will be, let's call it X, that there is going to be some loop, not necessarily loop, but some extended things on the way, and then it returns back to the X, and then it continues to the destination vertex without repeating things. So from U to X, things are not repeated, and from this, it does some unnecessary stuff between X and getting back to X, and then after X to V, things are again not repeated. So this thing, instead of exiting X into some direction that's unnecessary and then coming back, this thing can be just connected, that this whole thing can be removed. So if this is removed, we remade a walk into a path. And that is the reason why every walk can become a path.